Good morning, everyone. I am Akshata Patil from AIDS Department of Sharad Institute of Technology, College of Engineering. So today I am going to explain Banker's algorithm, which is a deadlock avoidance algorithm used in the operating system. So first let us understand what a deadlock is. So a deadlock is a situation where multiple processes are waiting for resources and that resources are held by the other resources and none of them can proceed further. So in a simple word we can say all processes become stuck permanently. So this is the situation of deadlock. So no process can proceed further. Okay, so to avoid such situations, the operating system uses deadlock avoidance techniques. One of the most important technique is Banker's algorithm. So today we are going to discuss about the Banker's algorithm, which is the deadlock avoidance technique. So the Banker's algorithm technique is introduced by Dijkstra and it is called as a Banker's algorithm because it works similar like a bank system. So, as we know, a bank gives loans to customers only if it can safely satisfy all customers in the futures. Okay, so same like that, the operating system allocates resources only if the system remains in a safe state. So now let us understand some important terms used in Banker's algorithm. So these are the requirements of the Banker's algorithm. So there are four very important concepts in the Banker's algorithm and that are allocation, maximum, available and need. So let me discuss one by one. The first one is the initial allocation. So allocation means resources already assigned to the process. Okay, so we know that if any process want to complete its execution, it requires some resources. So initial allocation, it shows the already allocated resources to the process. The next term is a maximum. So maximum is the maximum number of resources that process required for the execution. Means it's a maximum need of the process to complete its execution. The next one is available. So available is the number of free resources currently available in the system. So let me consider there are four processes. We have already allocated some resources to that processes. But after allocating, some resources are remaining in the operating system which are free resources and that can be allocated to the processes who are requiring to the resources. Now last term is a need. So this is what the number of resources still needed for the each process. Just we have seen allocation means allocated process and this is what maximum need of that process. So how we are going to calculate the need of the process? So maximum minus allocation. So this is the current need of the process. So there is a process 1, it already having 2 resources, but the requirement is what? The maximum requirement is what? 4 resources. So how we are going to calculate the need? That 4 minus 2. So 2 is what? The current need of the process. So these are the very important points from the Banker's algorithm and we can call it as a data structures. So these are the data structures in the matrix format. The data is stored into Banker's algorithm. So now we will solve one example. So we are going to easily understand the concept of Banker's algorithm. So see here, considering the following example of a system, check whether the system is safe or not using Banker's algorithm and determine the sequence if it is safe. So before going to start solving this example, we will see what is the safe state. So now safe state or safe sequence is what? A safe sequence means all processes can complete execution without causing deadlock. So this is what a safe state. So if the system is in a safe state, we are going to find out the safe sequence. Now see, this is the example. Okay, so what are the given things in the exams? The number of processes. So here 5 processes are there from P0 to P4. Now this is what allocation. Just we have discussed about the allocation matrix. So what is the allocation? Now see here, A, B and C. These 3 are the different resources. Let me consider A is a printer, B is a scanner and C is a we can consider it as a tape. Okay, so and these are the instances of the resource. See here, the P0 already allocated resources are 0 instance of A, means there is a no printer provided to the P0 process. Now 1 instance of a B is allocated to P0, means 1 scanner is allocated to P0, and 0 instances of C means 0 instances of tape is allocated to the P0 process. Okay, so same like that, 2 instances of resource A is allocated to P1 and 0 resources are allocated to P1 of type B and C. Now 302, this is the allocation for P2. 211, this is the allocation for P3, and 002, this is the allocation for P4. So these are the allocated processes, already allocated processes to the P0 to P4 process. Now the second column shows the maximum need. So maximum need means these number of resources are required to process to complete its execution. Means see here in the example, the maximum need of the P0 process is 753, means 7 instances of A, 5 instances of B and 3 instances of C. From that we have already allocated 010 resources to the P0 process. Now see, this is the maximum need of the P1 process, that is 322. 3 instances of A, 2 instances of B, 2 instances of C. Now this is for P2 process. Maximum need is what? 902. Next, for the P3 process, 222. This is the maximum need. And for the last P4, the 433 is the maximum need of that process. Okay, so these are the given things in the example. Now consider this first row of the available matrix. So see here, 332 means what? There are some instances of A, B, C are in the operating system. Okay, so from that already we have allocated this much resources to the process. So 332 is the remaining process after allocating resources to the processes. Now the available resources are 332, means 3 instances of A, 3 instances of B and 2 instances of C. Now currently 332 resources are available in the operating system. Now we are going to find out the need of the process. So just we have discussed how to calculate the need of the process, maximum minus allocation. When we are going to subtract allocation from maximum need, we will get the current need of the process. Now see here, let me calculate it for the P0 process. So maximum need is 7, 5 and 3 and already allocated is 0, 1, 0. So we are going to calculate the need. So 7 minus 0. it's what? 7. 5 minus 1, it's a 4. And 3 minus 0, it's a 3. So, in short, for the process P0, 0, 1, 0 resources are allocated, but the need is 7, 5, 3, and currently it needs 7 instances of A, 4 instances of B, and 3 instances of C. So same like that, we have to calculate need for each and every process. So for the P1, maximum need is 3, 2, 2, but the allocated is 2, 0, 0. So the requirement is what? 3 minus 2, it's a 1. 2 minus 0, it's a 2. 2 minus 0, it's a 2 again. So the current need of the process P1 is 1, 2, 2. Now again for the P2 process, the maximum need is 902 minus allocation is 302. So we will get 600. So for the P3 process, the maximum need is 222. So see here, the requirement of P3 is what? 2 instances of A, 2 instances of B, and 2 instances of C. From that already we have given 2 instances of A, 1 instance of B, and 1 instance of C. So the requirement is what? Only B and C, because already we have given the 2 instances of 2 instances of A to the process 3. So 2 minus 2 is a 0, 2 minus 1 is 1, 2 minus 1 is a 1 again. Now we are going to calculate it for the last process, that is a P4. The maximum need is 433 and the allocated is 002, means no any instances of resource A and B are allocated to the P4. So 4 minus 0 is 4, 3 minus 0 is a 3, and 3 minus 2 is a 1. So this is what? This is the current need of the processes. Okay. So here we can see how many numbers of instances are required to the processes. But currently we have 3 instances of A, 3 instances of B, and 2 instances of C are freely available in the operating systems. Okay. So now we are going to find out this system is in a safe or in a unsafe state. So for that, first we will see the currently available resources in the operating system. So 3, 3 and 2, these are the available. Now the need of the P0 process is 743. So can we provide the resources from the available resources to the P0? No, it is not possible. Why? Because the need of the P0 is a 7, but we are having only 3 resources. Here again 4 instances are required, but we are having 3. So we are not going to allocate, or it is not possible to allocate available resources to the P0 process. Okay, so let me think about the second need, the need of P1 process. It is 1, 2, 2, and we are having 3, 3, 2. So here we can see we can allocate the required or needed resources to the process P1, because we are having the, we can say the more number of resources are available in the operating system than the need of the P1 process. So here we can write P1 in the safe sequence. Why? Because we can easily allocate the available resources to the process P1. So here we have written P1 in the safe sequence. Now see here, when we are going to allocate 1 to 2 resources to the P1 process, it will finish its execution. Yes, and after that this already allocated resource, that is 200, are again free. So we are going to add this allocated resource into the available resource. So see here, we are going to add this 200 into 332. So the 3 plus 2 will become 5, 3 plus 0 will become 3, and 2 plus 0 will become 2. Now the available resources in the operating system are 532. This is the updated count, because after completion of execution, this P1 is going to deallocate the allocated resources. So the count is updated count of the available resources. Now we are having 532 available resource. Now think about the next, that is the P2 process. The requirement of P2 process is what? 600. Now the requirement of B and C is what? 0. But the requirement of A is what? 6. But we are having only 5 instances of resource A. So we are not going to allocate these resources to the process 2. So again we will move towards the next process, that is the P3 process, and the requirement of P3 process is what? 0, 1, 1, and we are having 5, 3, 2. So we can easily allocate these available resources to the P3 process. So here again in the same sequence we are going to write P3. So we are going to allocate resources from this to the P3. So again after execution of the P3, these allocated resources are become a free resources. So we are going to add these allocated resources to the available resources. So available resources what? 532, and we are going to add 211. So 5 plus 2 will become 7, 3 plus 1 will become 4, and 2 plus 1 become 3. So now this is what? This is the updated count. This is what? The updated count of the available resources. Now again we are going to move forward. So now it's a P4 process. The requirement is what? 431, and we are having 743. So we can again easily allocate these available resources to the P4 process. Okay. So here we are going to write P4 in the same sequence. So again after completion of the P4 process, it will release these 2 instances of the resource C. So the updated count is what? 7 plus 0, 7, 4 plus 0, 4, and 3 plus 2 will become 5. Now this 7, 4, 5 is the updated count of the available resource. Okay. So now again we are going to think about the P0 process. The requirement is what? 7, 4, 3, and the available resources are 7, 4, 5. So we can easily allocate these available resources to the P0. So here we are going to write P0 in the same sequence. So this P0 is going to release this 0, 1, 0 resources. So the updated count will become 7 plus 0, 7, 4 plus 1, 5, 5 plus 0, again 5. So the available resources are 7, 5, 5. So which process is now remaining? It's a P2. The requirement is 600, and we are having 7, 5, 5. So again we can easily allocate these resources to the process P2. So here the last we are going to write the P2. See here, there is no any deadlock. Okay. So we can call it as a safe sequence, or we can call the operating system is in a safe mode. So now this 755, after execution, again P2 will release the allocated resources, that is 302. So the 7 plus 3 will become 10, 5 plus 0 will become 5, and 5 plus 2 will become 7. So total 10 instances of A, 5 instances of B, and 7 instances of C are available in the operating system. So there is no any deadlock. we can easily allocate the available resources to the processes to complete its execution. And here this is the SAPE sequence. So first we have to allocate resources to the P1 process, then P3, then P4, after that P0, and lastly we are going to allocate resources to the P2. So this is the example of Banker's algorithm. So now we will see the advantages and disadvantages of the Banker's algorithm. The first advantages. The biggest advantage of Banker's algorithm is that it prevents deadlock by avoiding unsafe state. It allocates resources only when the system remains safe condition. The another advantage is what? It's safe and systematic resources allocation. In the Banker's algorithm, the resource allocation is what? Safe and systematic. This helps the operating system to maintain the stability and the reliability. Again, it also allows multiple processes to execute safely without conflict over resources. Okay. In addition, Banker's algorithm can identify unsafe condition before an actual deadlock occurs. So these are some advantages of the Banker's algorithm. Now we will see the disadvantages of Banker's algorithm. The one major disadvantage is that what? The algorithm requires prior knowledge of the maximum resource requirement of every process. So the processes must declare the maximum resource requirement before and cannot be changed during execution. The another disadvantage is that it becomes complex and difficult to implement in a large system. So just we have seen the example for the 5 processes, but we know that there are multiple processes are executing in the operating system. So whenever there are the maximum number of processes, it is very difficult to execute with the Banker's algorithm. Now sometimes resource utilization becomes lower because the system allocates resources very carefully. Also, Banker's algorithm is not suitable for systems where processes and resource requirement change dynamically. So this is about the Banker's algorithm. Thank you.